Welcome to our third video on stoichiometry calculations involving mass either at the beginning or the end or both of the calculations. In these calculations, we're going to be doing problems that are more realistic because we can measure mass directly. And we're going to go back to chapter 11 where we used molar mass to convert between mass and moles, and we're going to be doing a lot of that in this unit. And we're going to find that the molar mass, the mole-to-mole conversions using the coefficients from the balanced chemical equations are still going to be central to the calculations. We're just going to wrap the mass to moles and moles to mass around the outside of the two calculations. All right, so there's three different ways we can think about these problems. One is which we're starting with the mass. Now, the process is always going to look familiar. The process is always going to be involving dimensional analysis. And in that dimensional analysis, we're going to have a given and a wanted as we had before. But this time, the given and the wanted are going to be maybe different units. We might have the wanted in units of moles. We might have the given in units of mass. But remember, we're always going to have both units and a substance when we have our given and our wanted. As before, we'll select the mole-to-mole ratio with the coefficients of the wanted over the given from the balanced chemical equation. So let's see how this calculation is going to work. We're first going to multiply, since we're starting, in this case, starting with mass, we're going to multiply the mass of the given by 1 mole over the molar mass of the given. We're then going to continue the dimensional analysis by multiplying by the mole ratio of the moles of the wanted over the moles of the given, where of course the B and the A are the coefficients of the wanted and given from the balanced chemical equation. So for the reaction, nitrogen and 3 hydrogen react to form 2 ammonia gas. Let's determine the number of moles of ammonia that are produced by reacting 16.2 grams of hydrogen with sufficient nitrogen. And again, that word sufficient is just there to mean that you can ignore the nitrogen. There's more than enough of it to go around. So the first thing we're going to do is set up our question mark, and the number of moles of the ammonia is equal to how many moles of 16.2 grams of hydrogen. Now we're going to go to our mass to mole calculation using the molar mass. 1 mole of hydrogen is 2.018 grams of hydrogen. Now something that's very important here. I want you to note that this number right here, this number is never going to be the coefficient in the balanced chemical equation, because the number of the mass in 1 mole, the molar mass, is always exactly 1 mole of that compound. So it's always going to be, the molar mass is going to be for 1 mole, not for the coefficient in the balanced chemical equation. But now, if we stopped here, we would have the moles of hydrogen, but let's keep going. Now we're going to go to the coefficients. We're going to take that 3 from the hydrogen and bring it down into the denominator, and we're going to bring the 2 from the ammonia and bring it into the numerator. Going to change that into our 2 moles of ammonia over 3 moles of hydrogen. And again, what's going to happen here is that the moles of the hydrogen and the moles of the hydrogen here are going to cancel out. That's going to leave us with moles of ammonia. And that's our desired answer. So we finish up with the math, and we get that we have 5.35 moles of ammonia as our result. Let's turn it around a little bit and see what happens if we end with mass. As before, we're going to identify the given quantity and the wanted quantity. In this case, the given quantity is going to be moles and the wanted quantity is going to be mass. We're going to select the mole ratio from the balanced chemical equation and set up the calculations. Since we're starting with moles of the given, we're going to end up multiplying immediately by the mole ratio of the B moles of the wanted over the A moles of the given. At this point, we're going to have the moles of the wanted, so we're going to multiply by the molar mass of the wanted over 1 mole, and we're going to end up with the mass of the wanted. Let's go back to the same reaction. And now we want to know what the mass of N2 is required to fully react with 23.8 moles of hydrogen. Set up our start for the dimensional analysis, number of grams of nitrogen and the number of moles of hydrogen. Now, go right to the mole-to-mole ratio. Since we have moles here, don't go back. If you go back to calculate mass, you're going the wrong way. Do not go backwards. You're going the wrong way if you do that, and it'll mess you up a lot. So let's go to the mole ratios. We have the 3 in the hydrogen again. Put that in the denominator. We have the 1, implied 1 now in front of the nitrogen. Put that in the numerator. Change that to our mole ratio. 1 mole of nitrogen over 3 moles of hydrogen. The moles of hydrogen are going to cancel out as they did before, leaving us with moles of nitrogen. But we wanted to have the mass of the nitrogen. We're looking for mass of the nitrogen. So we're going to now take the molar mass of the nitrogen, and we're going to put the moles in the denominator because we want the moles of the nitrogen and the moles of the nitrogen to cancel out. Again, 1 mole of nitrogen in the denominator, multiplying by 28.02 grams of nitrogen. And our result comes out to be 222 grams of nitrogen. Now, more realistic problems, and you'll be doing this in the lab at the end of this week, is problems that start and end with mass. And that makes sense because we can measure mass of the reactant, we can measure mass of the product, and most of the mole-to-mole problems we're going to be doing are going to actually be mass-to-mass problems. Here's a little helpful flow chart to help you along the way. The mass of the given to the moles of the given, you're going to use the molar mass to do that. From the moles of the given to the moles of the wanted, you're going to use the balanced chemical equation. And then from the moles of the wanted to the mass of the wanted, you're going to use the molar mass of the wanted. Here's a new reaction for us. We're going to take 4 phosphorus, it's a solid, and 5 oxygen gas molecules, and we're going to react to form P4O10 as a solid. And we want to know how many grams of oxygen are required to completely react with exactly 39.2 grams of phosphorus. As before, we've got that dimensional analysis that's going to guide us. Our dimensional analysis is going to get us through this. First, multiply the mass of the given, here's the mass of the given, by 1 over the molar mass of the given, the phosphorus. Now again, remember, the molar mass is for 1 mole. This part of the equation, this part of the calculation doesn't really care how many moles of phosphorus there are in the balanced chemical equation. We're just finding how many moles of phosphorus we have. So we're going to take that, we're going to cancel the grams of phosphorus. That's going to leave us with the number of moles of phosphorus. Now we go to the balanced chemical equation. We take that 4, bring it down to the denominator, take the 5 from the oxygen, bring it down into the numerator, change this over to our mole-to-mole ratio, and we're multiplying by now the B moles of the wanted over the A moles of the given. B moles of the wanted now in the numerator, the A moles of the given in the denominator, cancel out the moles of the phosphorus. That leaves us with moles of oxygen. We wanted grams of oxygen, so the last step we have to do is multiply by the molar mass of oxygen over 1 mole. 32.00 grams of oxygen over 1 mole. The moles of oxygen cancel out, and they give us 50.6 grams of oxygen. As I said before, if you're given the moles of the given, don't convert. You're going to start at the second step. If you go back and calculate the grams, the mole-to-mole ratio is not going to work out for you. So again, if you're given the moles of the given, you're going to start at that second step and go right into the mole-to-mole ratio. All right, so let's let you give it a try. I'll turn off the recording in a moment, and you have a little chance to do the calculation. And when you're done, restart the recording and check out how you did. All right, so hopefully you've done the work and you have an answer. Let's see how you did. First thing you want to do is set up the stoichiometry. This time we're going to use the railroad track method. Set up the dimensional analysis, starting with the mass of the benzene, 84.7 grams, C6H6. First thing we want to do is we want to get cancel out the moles of the, cancel out the grams of the benzene and get to moles of the benzene. So let's multiply by 1 mole of benzene over the molar mass. Remember, mass in the numerator means that we have to have mass in the denominator so they can cancel out. That leaves us with the moles of the benzene. Now we go to our balanced chemical equation. Benzene has a coefficient of 2. That's going to come down into the denominator. And the oxygen has a coefficient of 15. Yep, that's a pretty big one. That goes into the numerator. So we have 15 moles of oxygen over 2 moles of benzene. And let's go back and cancel out those moles of benzene. That leaves us with moles of oxygen. And we do the molar mass of oxygen, 32.00 grams of oxygen and 1 mole of oxygen. Cancel out those moles of oxygen. And did you get 260 decimal point for significant figures grams of oxygen? All right, so this is the end of this unit. Please go on and read section 12.2 in the book, and we will see you in class for the practice.